Imagine a piece of dark coal the size of a 40-story office building silently flying across a sunlit room at 24 times the speed of a bullet. While billions of people are having breakfast, commuting to work, or sleeping peacefully in their beds, that exact mountain of rock is passing through the empty space between our weather satellites and our upper atmosphere. Not a single radar warning was issued, not a single telescope raised the alarm, and not a single computer algorithm realized what was happening until the object was already moving away from us. Human civilization missed a direct impact by less than 40 minutes, completely unaware that a regional catastrophe had just grazed our planet. If you are drawn to the unexplained mysteries of deep space and want to discover the real facts without false drama, take a second right now to subscribe, so you can join our community on every new scientific journey. To truly understand how a skyscraper-sized asteroid can sneak past the most advanced telescope networks on Earth, we have to look closely at how planetary tracking actually works. For over 50 years, traditional astronomy relied on ground-based optical observatories perched high on quiet mountain peaks around the globe. Astronomers would point giant lenses into the night sky, taking thousands of sequential photographs of star fields. If a tiny speck of light moved across the still background of distant stars between two photos, computers flagged that object as a moving asteroid. An asteroid is essentially a leftover building block from the formation of our solar system more than 4.6 billion years ago. When the sun and planets condensed out of a giant cloud of gas and dust, vast amounts of rocky and metallic debris never pulled together into a full planet. The vast majority of this leftover material settled into a broad, stable band between Mars and Jupiter known as the main asteroid belt. Millions of rocks orbit quietly in this belt, staying hundreds of millions of kilometers away from Earth. However, the main asteroid belt is not a static or peaceful place over long spans of time. The immense gravity of Jupiter, the largest planet in our solar system, acts like an invisible gravitational pendulum. When asteroids drift into specific resonant zones within the belt, Jupiter pulls on them repeatedly, gradually stretching their circular orbits into elongated oval paths. Eventually, a single close pass near Jupiter can fling an asteroid completely out of the main belt, hurling it straight into the inner solar system where Earth, Venus, and Mercury travel. Astronomers classify these dislodged space rocks as near-Earth objects, or NEOs for short. Because an impact from one of these objects can deliver immense destructive power, international space agencies built specialized monitoring systems. Projects like the Catalina Sky Survey in Arizona, the Pan-STARRS telescopes in Hawaii, and the Atlas system were funded to scan the heavens every single clear night. The public was assured that any rocky intruder large enough to cause catastrophic damage would be identified months or even decades before it ever came close to Earth. These early warning systems rely heavily on complex software algorithms that compare images taken 30 to 45 minutes apart. When an automated camera photographs a patch of sky, computers automatically subtract all known stars, galaxies, and previously mapped asteroids from the digital image. If an unidentified point of light remains, the system alerts human observers to confirm the discovery and calculate an initial orbital trajectory. For this system to work reliably, astronomers must be able to observe the object over multiple nights. By taking measurements across several days, mathematicians can calculate the precise curve of the asteroid's path around the Sun. This process, known as orbit determination, allows scientists to project where the rock will be 10, 20, or even 50 years into the future with remarkable accuracy. That widespread sense of planetary security was shattered without warning when an asteroid officially cataloged as 2019, swept silently over our heads. The asteroid was estimated to be between 130 and 140 meters across, making it as large as a full 40-story office building or a giant sports stadium. When it crossed our orbital path, it passed within 70,000 kilometers of Earth's surface, which is an extraordinarily narrow gap in astronomical terms. To grasp just how close 70,000 kilometers really is, consider the distance between the Earth and our moon. The moon orbits our planet at an average distance of about 384,000 kilometers. Asteroid 2019. Flew inside 1/5 of that distance. If you imagine a scale model where the Earth is the size of a basketball and the moon is a tennis ball sitting 30 feet away, this 40-story rock flew just 6 feet away from the surface of the basketball. What troubled scientists was not merely the close physical distance, but the total failure of early detection systems. Standard planetary defense models predicted that an object measuring over 100 meters across would shine brightly enough in night sky surveys to be discovered several weeks before approaching Earth. That expected multi-week window would give emergency agencies ample time to calculate the exact impact footprint, notify civil authorities, and coordinate large-scale evacuations of coastal or urban areas. Instead, the actual timeline of discovery exposed a massive blind spot in global monitoring. The automated sky scanning networks missed the incoming rock entirely as it crossed deep space. Observatories in Brazil only logged faint positional images of the object when it was already hours away from its closest point. In fact, Many major tracking centers did not even confirm the asteroid's orbit until it had already crossed Earth's path and was traveling away from us back into the void. The root cause of this catastrophic failure was not broken cameras or computer errors, it was the simple geometry of the solar system. Asteroid 2019. OK approached Earth directly from the direction of the sun. Just as a driver cannot see a pedestrian when driving straight into a blinding sunrise, Earth-based optical telescopes cannot look into the daytime sky without their delicate light sensors being completely overwhelmed by intense solar radiation. The sun acted as a perfect cloaking device, hiding a skyscraper of rock in pure light. Every optical telescope on the planet is bound by the day and night cycle. When the sun rises, ground telescopes must close their protective dome doors to prevent delicate digital sensors from burning out under direct sunlight. This creates a permanent half-sky blind spot that surrounds our planet at all times. Any cosmic body traveling on an orbital trajectory that originates from the direction of the sun can fly straight toward Earth without ever being photographed by a nighttime survey telescope. Even during the brief twilight hours just after sunset and right before sunrise, pointing a giant telescope near the horizon remains extremely difficult. The thick layer of Earth's atmosphere near the horizon bends, distorts, and scatters sunlight, creating heavy visual noise that drowns out the faint signatures of distant space rocks. Because of this natural atmospheric wall, asteroids coming from inner solar orbits remain effectively hidden until the very last moment. Have you ever considered how vulnerable our planet remains to objects approaching from the sunlit side of our sky? Drop a quick comment below with your thoughts on our current sky surveys, and hit the like button if you want more deep investigations into real cosmic phenomena. When orbital specialists downloaded the raw positional logs to reconstruct the asteroid's path, the mathematical figures revealed even more shocking details. Most near-Earth asteroids cruise through space at relative velocities between 12 and 16 kilometers per second. However, asteroid 2019, OK, was moving with an exceptionally steep trajectory that accelerated its velocity to over 24 kilometers per second, which translates to more than 86,000 kilometers per hour. To understand that kind of velocity in everyday terms, a bullet fired from a high-powered military rifle travels at about 1 kilometer per second. Asteroid 2019. OK was moving 24 times faster than a rifle bullet. At that speed, the rock could travel from the surface of the moon to Earth in just 4 hours, or travel across the entire continental United States from coast to coast in less than 3 minutes. When an object of that size moves at such an extreme velocity, the physics of kinetic energy turn it into a weapon of staggering power. Kinetic energy is the energy of motion, and in physics, it increases with the square of the velocity. That means doubling the speed of an asteroid does not just double its destructive punch, it multiplies its destructive energy by 4 times. At 24 kilometers per second, the kinetic energy stored inside this single rock was astronomical. Planetary physicists calculated that if 2019 OK had struck Earth's atmosphere, the sudden atmospheric friction would have compressed the air in front of the rock into a superheated pocket of plasma. The asteroid would have detonated in midair as a massive airburst, releasing an explosive energy equal to approximately 10 megatons of TNT. That is equivalent to exploding more than 600 Hiroshima-sized atomic bombs simultaneously in a single localized flash. An airburst of that scale produces a supersonic shockwave that travels outward in all directions, shattering reinforced concrete structures, tearing down power grids, and stripping forests to bare earth across hundreds of square miles. The intense thermal flash generated during the explosion would instantly ignite wooden structures, vehicles, and vegetation across an entire metropolitan region, turning a thriving city into a field of burning rubble in less than 5 seconds. To understand what a mid-air asteroid explosion looks like in real life, scientists often point to historical events like the Tunguska explosion of 1908. In that event, an asteroid estimated to be only 50 to 60 meters wide exploded over a remote forest in Siberia, flattening 80 million trees across 2,000 square kilometers with the force of 12 megatons. Asteroid 2019. OK was more than twice the size of the Tunguska object, meaning its destructive footprint would have covered a significantly larger land area. Even more recently, in 2013, a tiny space rock measuring only 20 meters wide exploded over the city of Chelyabinsk in Russia. That relatively small rock produced a shockwave that blew out windows in thousands of buildings, collapsed the roof of a factory, and injured more than 1,500 people, mostly from flying shards of glass. The energy of the Chelyabinsk blast was roughly 500 kilotons. Asteroid 2019. OK carried 20 times the destructive potential of Chelyabinsk. If an asteroid the size of 2019 OK entered the atmosphere over a major modern city, the sequence of destruction would unfold faster than emergency dispatchers could react. In the first fraction of a second, the meteor would outshine the sun, creating a blinding flash that would cause temporary or permanent blindness to anyone looking in its direction. Within 3 seconds, Thermal radiation would ignite fires across rooftops, asphalt roads, and trees across a 30-kilometer radius. A split second later, the hypervelocity shock wave would strike the ground with immense overpressure. Modern skyscrapers with glass facades would disintegrate into clouds of lethal flying debris, residential neighborhoods would be flattened into kindling, and highway overpasses would collapse under the sudden downward force. The entire infrastructure of a modern capital city would be completely incapacitated in the blink of an eye. This terrifying calculation forced NASA and international space organizations to confront an unsettling truth about their catalog of near-Earth objects. For years, public communications highlighted that astronomers had successfully found and cataloged over 95% of all near-Earth asteroids that are 1 kilometer or larger. A 1-kilometer asteroid is large enough to cause global climate collapse and threaten the survival of human civilization. So finding them was rightly celebrated as a major triumph. However, the internal data tells a very different story when it comes to medium-sized asteroids like 2019. Okay, objects between 100 and 300 meters across are commonly referred to as city killers because, while they will not wipe out all life on Earth, they possess more than enough energy to annihilate an entire modern city and its surrounding suburbs. Out of the estimated 25,000 city killer asteroids orbiting in our solar neighborhood, scientists have identified fewer than 40%. That means there are still more than 15,000 undiscovered city killer asteroids crossing Earth's orbital path right now. These objects are made of dark carbonaceous rock, silicate minerals, or dense iron-nickel alloys. Many of them reflect less than 5% of the sunlight that strikes their surface, making them darker than a lump of charcoal or fresh asphalt on a highway. Finding a dark, 400-foot rock against the deep black canvas of space is one of the hardest observational challenges in modern science. Astronomers measure an asteroid's brightness using a scale called absolute magnitude. The darker and smaller an asteroid is, the higher its magnitude number and the harder it is to see. Many carbonaceous asteroids, which contain large amounts of organic carbon compounds, absorb nearly all visible light that falls on them. When these dark bodies travel through space, optical cameras on Earth see almost nothing, leaving astronomers completely blind to their presence until they are right on top of us. Did you realize that over 15,000 large asteroids capable of leveling an entire metropolis are still completely unmapped in our solar system? Tell us your thoughts in the comments section below, and remember to subscribe to keep uncovering deep scientific truths that rarely make the evening news. This fundamental visibility challenge led researchers to re-examine another legendary space rock that has occupied planetary defense discussions for over 2 decades, the infamous asteroid Apophis. When astronomers at the Kitt Peak National Observatory first logged the coordinates of Apophis in June 2004, early computational models produced a calculation that sent shockwaves through the global scientific community. The data showed a 2.7% probability that Apophis would hit Earth on April 13, 2029. In the world of orbital physics, a 3% chance of a collision with an object of this magnitude is an unprecedented emergency. To put that in perspective, the standard threshold that triggers high-level international planetary defense protocols is a collision probability of just 1 in 10,000. A chance of nearly 1 in 37 was so high that it forced observatories around the world to drop their regular research schedules and focus exclusively on tracking Apophis across the sky. To understand why the discovery of Apophis caused such intense concern among planetary scientists, we must look at its physical dimensions and composition. Apophis is an elongated peanut-shaped asteroid measuring approximately 340 meters across its longest axis. That makes it wider than the height of the Eiffel Tower in Paris, taller than the Empire State Building, and heavier than 60 million metric tons of solid rock. If an asteroid of that massive bulk collided with Earth, the outcome would far exceed the local destruction of a city killer. An impact by Apophis would carve an impact crater over 5 kilometers wide and hundreds of meters deep, throwing millions of tons of pulverized rock and vaporized crust directly into the upper atmosphere. The resulting regional shockwave would level buildings across entire countries, while the heat from the impact plume would ignite wildfires across millions of acres. Furthermore, if an object the size of Apophis slammed into an ocean, the immense displacement of water would generate towering tsunamis hundreds of feet high. These monstrous waves would travel across entire oceanic basins at the speed of a commercial jetliner, obliterating coastlines and maritime infrastructure across thousands of miles of populated shores. The economic, humanitarian, and environmental toll of an ocean impact would destabilize global trade and displace hundreds of millions of people. In addition to physical destruction, the fine dust and particulate matter thrown into the upper stratosphere by an impact of this scale would linger for months. This high-altitude dust cloud would scatter incoming sunlight, leading to significant regional cooling, shortened agricultural growing seasons, and widespread crop failures. The secondary humanitarian crisis caused by agricultural collapse would ripple across the global economy long after the initial blast cleared. Faced with this potential catastrophe, astronomers around the planet mobilized giant radar tracking antennas to pin down Apophis's precise orbit. Giant dish antennas, such as the Goldstone Deep Space Communications Complex in California and the former Arecibo Observatory in Puerto Rico, blasted powerful microwave radar beams directly at the moving asteroid. By measuring the tiny time delay and frequency shift of the returning radio echoes, engineers calculated the asteroid's distance and velocity down to fractions of a millimeter per second. After years of meticulous radar tracking and orbital refining, scientists were able to rule out a direct collision for the year 2029. The data confirmed that Apophis will safely miss our planet. However, the exact mechanics of that upcoming 2029 flyby reveal a breathtaking and dangerous cosmic event that will permanently alter the asteroid's future trajectory. On April 13, 2029, Apophis will sweep past Earth at a distance of just 32,000 kilometers above our surface. To understand how exceptionally close that is, consider that our highest telecommunications and weather satellites operate in what is called geostationary orbit, located 35,786 kilometers above Earth. Apophis will literally pass beneath the orbit of our outer satellites, visible to billions of people across Europe, Africa, and Asia, with the naked eye as a bright point of light moving across the night sky. When a 60-million-ton asteroid passes that close to a massive planet like Earth, powerful gravitational forces come into play. Earth's immense gravity will pull unevenly on different parts of the asteroid's rocky body. The side of Apophis facing Earth will experience a significantly stronger gravitational pull than the side facing away. This uneven pull produces severe gravitational stretching forces known as tidal stresses. Advanced supercomputer models developed by Planetary geologists show that these tidal stresses will violently shake Apophis as it screams past Earth. The asteroid will experience powerful internal seismic tremors, commonly referred to as asteroid quakes. Huge boulders resting on its surface will roll and tumble, layers of surface dust will be lifted into space, and the internal structure of the asteroid may crack and shift under the strain. More critically, passing through Earth's intense gravitational well will bend the trajectory of Apophis like a curveball thrown by a baseball pitcher. The encounter will dramatically alter its orbital period around the Sun, changing it from an Aten-class asteroid whose orbit stays mostly inside Earth's path to an Apollo-class asteroid whose orbit spends more time outside Earth's path. This gravitational deflection means that scientists must recalculate all of Apophis's future close encounters for centuries into the future. This gravitational reshaping of an orbit is deeply sensitive to what astronomers call gravitational keyholes. A gravitational keyhole is a tiny, invisible region of space, often only a few hundred meters across, where a planet's gravity can alter an asteroid's orbital path by the exact mathematical amount required to cause a direct collision on a subsequent orbit years later. During the 2029 flyby, if Apophis passes through one of these tiny keyholes, it could be set on a direct collision course for a return visit in 2036 or 2068. What makes these long-term trajectory calculations so remarkably complex is a subtle physical phenomenon known as the Yarkovsky effect. The Yarkovsky effect is a tiny, persistent push that occurs when an asteroid absorbs energy from the Sun. As an asteroid rotates in the vacuum of space, its sunlit daytime hemisphere heats up, and when that heated surface rotates into the cold shadow of space on the nighttime side, it slowly radiates that thermal energy back out as infrared radiation. This outward emission of thermal photons acts exactly like a microscopic rocket thruster, firing continuously against the asteroid's surface. While the force generated by the Yarkovsky effect is extraordinarily weak, equivalent to the weight of a few sheets of paper resting in your hand, it never stops pushing. Over decades and centuries across billions of miles of space travel, this gentle thermal recoil can push a massive asteroid thousands of kilometers off its mathematically predicted path. Do you think subtle forces like thermal radiation make long-term space tracking too unpredictable to rely on? Share your perspective in the comments below and consider giving the video a quick like if you appreciate detailed, accurate scientific explanations. Because natural forces like the Yarkovsky effect and planetary gravity can constantly alter an asteroid's course, scientists realized that passive observation from Earth would never be enough to guarantee our long-term planetary safety. Humanity needed to find out if it was physically possible to alter the orbit of an incoming space rock intentionally. This urgent scientific question gave birth to NASA's groundbreaking double asteroid redirection test, universally known as the DART mission. The DART mission was humanity's very first active planetary defense test designed to alter the motion of a celestial body in space. Launched in late 2021, the mission targeted a binary asteroid system consisting of a larger primary asteroid named Didymos, measuring about 780 meters across, and a smaller companion moonlet named Dimorphos, measuring approximately 160 meters in diameter. Dimorphos was selected as the target for this historic test for several reasons. First, the entire Didymos system was more than 11 million kilometers away from Earth and presented zero threat of hitting our planet, ensuring the experiment was completely safe. Second, because Dimorphos was orbiting around Didymos like a tiny moon, astronomers could use ground-based telescopes to measure even the slightest changes in its orbital period with incredible precision. The engineering team built a robotic spacecraft weighing approximately 600 kilograms, about the size and weight of a standard vending machine or a small golf cart. The mission concept was pure, straightforward physics. Steer the spacecraft across 11 million kilometers of deep space and crash it directly into the center of Dimorphos at a hypervelocity of over 22,000 kilometers per hour. This technique is known in aerospace engineering as kinetic impact deflection. Leading into the mission, global astrophysicists ran complex mathematical simulations to predict how much the impact would slow Dimorphos down. The general consensus across the planetary defense community was that slamming a 600 kilogram craft into a 5 billion kilogram asteroid would produce a subtle change. Experts predicted that the collision would shorten the asteroid's 11-hour and 55-minute orbit by approximately 7 to 10 minutes. A 10-minute change would be considered a major scientific success. On September 26, 2022, the DART spacecraft locked its onboard optical navigation cameras onto Dimorphos and steered itself straight into the asteroid's rocky face at full speed. Spacecraft cameras beamed back real-time images showing giant boulders and rocky plains growing larger and larger until the final frame cut to static at the moment of catastrophic impact. When global observatories and deep space telescopes, including the James Webb Space Telescope and the Hubble Space Telescope, analyzed the aftermath of the crash, the data stunned every orbital scientist on Earth. The impact had not shortened Dimorphos' orbit by 7 minutes. It had changed the orbital period by an incredible 33 minutes, more than 3 times the highest predictions made before the test. The data revealed that the kinetic impact did not simply transfer the momentum of the moving spacecraft to the asteroid. The violent crash blasted thousands of tons of pulverized rock, dust, and boulders backward into the vacuum of space, creating a massive glowing debris tail that stretched over 10,000 kilometers behind the asteroid. This explosive ejection of material acted like a powerful rocket thruster firing in reverse, delivering far more kinetic momentum to the asteroid than the spacecraft itself. However, the deep analysis of the DART impact data revealed a critical technical reality that every planetary defense planner must now account for. The massive deflection worked so effectively because Dimorphos was not a solid, monolithic block of hard rock. Instead, Dimorphos was a rubble pile asteroid, a loose agglomeration of thousands of boulders, gravel, and dust, held together only by microscopic gravity, essentially resembling a floating pile of cosmic rubble. When the spacecraft slammed into the rubble pile, the energy was absorbed through the loose material, blowing away a vast crater and permanently changing the physical shape of the entire asteroid. But what if an incoming asteroid on a collision course with Earth is not a loose pile of gravel? What if it is a solid, dense slab of metallic iron and nickel, like the fragments of ancient protoplanetary cores that drift through our solar system? A kinetic impactor hitting a solid metallic asteroid would behave very differently. Instead of blasting off thousands of tons of ejecta to create a powerful rocket recoil, a spacecraft crashing into solid iron might only leave a shallow dent, transferring significantly less momentum. This means that before humanity can launch a deflection mission to save a city or continent, we must know the exact structural composition of the incoming threat. Beyond kinetic impactors, aerospace engineers are actively researching other theoretical methods to divert dangerous space rocks if kinetic crashing proves insufficient. One of the most promising concepts is the gravity tractor. A gravity tractor is a heavy, unmanned spacecraft that flies alongside a threatening asteroid for months or years without ever touching it. By using the mutual gravitational attraction between the spacecraft and the asteroid, the craft can slowly pull the asteroid off its trajectory. While the gravitational force between a spacecraft and a giant rock is minuscule, firing ion thrusters over several years can accumulate enough of a deflection to make the asteroid miss Earth entirely. The huge advantage of a gravity tractor is that it works regardless of whether the asteroid is a loose rubble pile or solid iron block. Another advanced concept involves directed thermal ablation, where a spacecraft equipped with powerful solar concentrators or high-energy lasers focuses intense heat onto a single spot on an asteroid's surface. The heat vaporizes the surface rock into gas jets that blow outward into space. These venting gas jets act like natural rocket thrusters, pushing the asteroid in the opposite direction and steadily nudging it off its collision path over time. For truly massive threats with short warning times, scientists have modeled nuclear standoff detonations. In this scenario, a nuclear device is detonated a few hundred meters away from the asteroid rather than directly on its surface. The intense X-ray radiation from the nuclear blast superheats a thin layer of the asteroid's surface rock, causing it to vaporize and blow off violently into space. The resulting rocket-like recoil pushes the entire asteroid off course without shattering it into thousands of uncontrolled fragments. If our planetary defense teams spotted a solid metallic asteroid heading toward Earth with only 3 years of advance warning, which method do you think our global leaders should choose? Write your thoughts in the comments section below, and take a moment to subscribe so you can stay informed on all future deep space defense discoveries. To eliminate this life or death guesswork, space agencies across the globe are constructing an advanced fleet of specialized deep space reconnaissance instruments. The most important of these new missions is NASA's Near-Earth Object Surveyor, or NEO Surveyor, an advanced space telescope purpose-built to hunt down hidden asteroids that evade ground-based optical cameras. Unlike telescopes on Earth that search for the visible light reflected by asteroids, NEO Surveyor will operate in deep space outside Earth's atmosphere, using high-sensitivity thermal infrared detectors. Because every space rock absorbs radiant energy from the sun and emits it back out as heat, even an asteroid that is pitch black will glow brightly in infrared wavelengths. NEO Surveyor is engineered to search specifically in the region of the sky closest to the sun, directly targeting the dangerous blind spot that hid asteroid 2019. Okay. Over its baseline mission, this orbital observatory is projected to discover and catalog more than 90% of all remaining near-Earth objects larger than 140 meters across, effectively mapping the hidden city killers that currently drift through our orbital neighborhood. The telescope will sit in a special gravitational balance point between the Earth and the Sun, known as the L1 Lagrange point. From this stable deep space vantage point, NEO Surveyor can look back toward Earth's orbital path continuously, scanning both the sunlit and dark regions of our space neighborhood without atmospheric interference, daylight restrictions, or weather interruptions. Simultaneously, international partners are launching specialized reconnaissance spacecraft directly toward Apophis to study it up close before and after its historic 2029 close approach. NASA has redirected its OSIRIS-REx spacecraft, newly renamed OSIRIS-APEX, to rendezvous with Apophis shortly after it passes Earth. The spacecraft will orbit the asteroid, map its changing surface features, and even fire its thrusters near the surface to stir up loose dust and reveal the internal geology beneath. The European Space Agency is also preparing the Ramses mission, a dedicated spacecraft designed to arrive at Apophis before it reaches Earth. By observing the asteroid before, during, and after its intense gravitational interaction with our planet, Ramses will provide humanity with an unprecedented real-time look at how planetary tidal forces reshape a massive celestial body. These synchronized missions represent a profound transformation in the entire history of life on our planet. For over 4 billion years, Earth has orbited inside a dynamic, unpredictable cosmic shooting gallery. Giant rocks and comets have repeatedly struck our world, altering planetary geology, triggering global mass extinctions, and rewriting the evolutionary tree of life. 66 million years ago, a 10-kilometer-wide asteroid slammed into the shallow waters off the coast of the Yucatan Peninsula in Mexico. The resulting explosion unleashed the energy of over 100 million megatons of TNT, triggering global firestorms, mega tsunamis, and a years-long impact winter that blocked the sun and wiped out the dinosaurs alongside 75% of all plant and animal species on Earth. The dinosaurs lived on this planet for over 160 million years, yet they had no telescopes to scan the dark sky, no mathematics to calculate orbital mechanics, and no engineering capability to build spacecraft to protect their world. When disaster fell from the heavens, they were entirely powerless to change their fate. Today, for the first time in the 4.6 billion-year history of Earth, a living species has developed the scientific understanding, the technological tools, and the collective willpower to look up into the void of space, identify incoming cosmic hazards millions of miles away, and physically push them off a collision course with our home, the unexpected flyby of asteroid 2019. Okay, and the impending arrival of Apophis are not reasons for fear, but powerful calls to scientific vigilance. They remind us that our planet is a precious, fragile blue sanctuary traveling through a vast and energetic cosmos. Every tracking radar we build, every infrared space telescope we launch, and every deflection test we conduct is an essential step toward ensuring that human civilization continues to thrive on this world for generations to come. As we look up at the quiet night sky, we are not just passive spectators watching the universe unfold from afar. We are active guardians of our homeworld, using science, curiosity, and engineering to build a permanent planetary shield around the only home humanity has ever known. If this deep, comprehensive look into the hidden reality of asteroid tracking and planetary defense gave you a new perspective on our place in the cosmos, please take a moment to subscribe to the channel. Click the notification bell so you never miss a new deep space breakdown. Drop a comment below telling us what space mystery we should cover next, and share this video with a friend who loves real science. Thank you so much for watching. And stay curious as we continue exploring the greatest mysteries of our universe together.